So this little video that I'm making today is kind of the next step after we draw the Bohr diagrams. So just a little bit of a review of what you did yesterday when drawing Bohr diagrams is we needed to draw a diagram that represents the atom. So we need our periodic table, and I'm hoping that you realized from yesterday's lesson that the Bohr diagram can be easily drawn if we look at what period the element is in and we look at what group the element is in. All right? So hopefully from yesterday, if you recall, you learned that if the element was in period 1, like hydrogen, helium, it would have only one orbit. And if the element was in period 2, let's say like nitrogen, it would have 2 orbits. Period 3, 3 orbits. Excellent. So the period number is going to tell us how many orbits it has. The number of elements in each period tells us how many electrons go in that orbit. So in period 1, only 2 electrons go in that orbit, and that orbit is then full. In period 2, 8 electrons go in that orbit, and then that period is, that orbit is full. Also 8 in 3. And then I told you to stop at calcium, and that's because the orbits get very complicated in the transition metals. That's something you will learn in grade 12. All right, so let's do a quick little review. Let's say that I wanted to draw the Bohr diagram for phosphorus. All right, it is in the 3rd period, which means it's going to have 3 orbits. Now remember, the first circle is our nucleus, and that tells us how many protons are in the nucleus and how many electrons. And phosphorus is atomic number 15, so it has 15 protons in the nucleus. So I write a 15 in the nucleus. Again, it's in period 3, so I'm going to write 3 orbits. This is a little big, but that's okay, you get the idea. So there's 3 orbits, and the first orbit has 2 electrons. All right, and remember, electrons like to pair up when they have to. They don't like to pair up that much, because remember, they're both negative. They will repel each other away. But if they have to, they will pair up. In the second orbit, there is 8 electrons. And remember, I would have said yesterday, it's kind of like bedrooms, where siblings have to share bedrooms, and they wouldn't want to if they didn't have to. So the first 4 go into their own bedrooms, 4 bedrooms, 1, 2, 3, 4. And then the next 4, they have to share a room, 5, 6, 7, 8. So there's our 8 electrons in the second orbit. And the other thing that hopefully you learned yesterday was that the number of electrons in the last orbit is determined by the group number. Now this is group number 15, all right? But we ignore the 1, and that's because we ignore those transition metals, and so 5, 1, 2, 3, 4, 5. Excellent. So that's the Bohr diagram for phosphorus. Now, that's a useful diagram. It tells us how many orbits there are, and it tells us how many electrons are in each orbit. But it's really a pain to draw. There's a lot of dots to draw there. And we've learned now that in chemistry that when chemical reactions take place, it's only these outer electrons, these 5 guys out here, these outer electrons, that are going to be doing anything. The ones on the inside, they stay put. They don't do anything. So we don't really need to draw all of these electrons. We only need really to draw the outer electrons. And that's what we do in a Lewis diagram. We only draw the outer electrons. All right, so let's go ahead and do that. So at this point, let's talk about what a Lewis diagram is. So you can write this down as a note. Lewis diagram. All right. And again, the name Lewis is just after the scientist who kind of created this. Lewis diagram, instead of putting the protons in the center, we put the element symbol in the center. All right, so the element symbol goes into the center. All right. The second thing is we we well, first we need to determine how many dots to put around it. So we determine the outer electrons from the group number. So we just need the outer electrons. These sometimes are called valence electrons. Valence. Valence is a fancy name for saying the outer electrons. It comes from the power to bond. It means the power to bond. And that's what bonding takes place. That's my next lesson. So we're going to have to determine the outer electrons from the group number. And then we put the electrons around, all right, around the symbol, all right, and first 4 are alone, and then pair up. All right, and that's kind of like what I was talking about yesterday, where that you can think of the spaces in the orbit as kind of bedrooms, and there's 4 bedrooms, and the first 4 get their own bedrooms, and then the 5th has to share. Now there's a special case. Hydrogen is special. All right, so special case here, right? Except hydrogen. Hydrogen only has 1 bedroom. Hydrogen only gets 2. Only 2 electrons. All right. So that's how we draw a Lewis diagram. All right, let's go back and take a look at our phosphorus for a moment. So there's our phosphorus right there. And if we didn't want to draw all those outer electrons, all those inner electrons, we don't want to draw this, that's too slow. We just want to draw the 5 outer electrons. So how would I do a Lewis diagram of phosphorus? Well, I just write the symbol P, all right? I go to the group number, we've already got it circled there, 15. I ignore the 10, 5. There's my 5 dots there. So I draw it around here like this. 1, 2, 3, 4, 5. And we don't even draw the orbit itself. We just draw the dots. So right there is a Lewis diagram for phosphorus. Let's go and draw a few more Lewis diagrams here. Let's move over to this page here. So I would have liked a periodic table. So what am I going to do? I'm going to take that. Come on. See if I can get a periodic table on this other page here. I'm going to bring this guy over to here. Let's see if it goes to the other page. Come on. You can do it. Nope, it didn't come over. Let's try one more time. Nope. Oh, there it is. There's my periodic table. Nice. All right. Let's make a periodic table. Good. Beautiful. So let's take a look at our table here. And let's draw some diagrams here. Just 1 second. My program is struggling. And I cannot do anything with that periodic table. Look at that silly periodic table there. Expand. Let's try another one. And that's a good one. See if I can make it bigger. Nice. Close that up. Move that out of the way. Get out of the way. Okay. All right. There we go. All right. So let's take a look at this periodic table here. Let's ignore this little periodic table hiding in the background. All right, so let's take a look at some Lewis diagrams. I apologize for that. That's the way technology works. So let's draw one for hydrogen. All right. So hydrogen is in group 1. We don't care how many orbits it has. It doesn't matter what period it's in this time, but it's in group 1. So I'm going to draw an H. Oops, let's use a pen. An H. It's in group 1, which means it only needs one dot, and there it is. That's a Lewis diagram for hydrogen. Easy. Let's jump across the way to helium. Now, helium is in group 8, but it's a special case, and that's because the first orbit only needs 2. So helium's diagram, I'm going to put it way over here, like it's on the other end of the periodic table. Remember, it's only got kind of one bedroom. There's 1 electron, and now 2 electrons. Now that's it for helium. Helium's done. That orbit is full. So that's a special case. So let's now work our way across the next period. So next we've got lithium. Lithium again is back in group 1. So lithium's going to be an Li, again with a single dot. All right? And if I move over to beryllium, it's in group 2. So beryllium is going to be a Be, and it's going to have 2 dots, except this time they get their own bedrooms. All right, nice. Now I'm going to put a little line here to represent the transition metals, and let's now go on to boron. Now boron's in group 13, B, but we ignore the 10, so 3. 1, 2, 3. All right? Next we have carbon. 1, 2, 3, 4. And then we have nitrogen in group 5. 1, 2, 3, 4, 5. All right, so there's a nitrogen with 5. Now I've run out of room here, obviously. I can do oxygen. It would have 6, and fluorine would have 7. But I'm going to draw a little squiggly line over here because I want to get all the way to neon. Neon is in group 18 or 8, and I'm going to put it down here. Neon. And neon is going to have, I'm in trouble because I'm on the end of my page, but let's see if I can do it. 1, 2, I can't draw over there. Let me see if I can fix it. I got to erase. I apologize. Erase, erase, erase. Let's try neon. Ne, 1, 2, 3, 4, 5, 6, 7, 8. There is neon. Okay, now neon is special, like helium, in that outer shell is full. All right, that outer shell is full. And that's why neon doesn't react, because its outer shell is full. Now this means that we can now draw the Lewis diagram for anything in any of the groups. All right, so let's zoom back out here a little bit, and let's take a look. Let's say that we wanted to draw a Lewis diagram for something like germanium, Ge, germanium. Notice it's under the carbon. It's in group 4, which means it will be drawn just like carbon. Ge, 1, 2, 3, 4. So even though it's in group 5, and we have, 1, 2, 3, 4, group 4, and we don't know how these electrons behave. What we do know is it behaves like carbon. So that's what puts them in the same family. They react similarly because they have the same number of outer electrons. So if I wanted a chlorine, for example, group 17, Cl. I don't have room over there, so I'm not going to draw it over there. 1, 2, 3, 4, 5, 6, 7. And you'll notice that chlorine has 1 unpaired electron. In other words, it's short 1 electron from being full. That's what makes chlorine so reactive. All right, and we'll talk about that in our next lesson. Chemical reactions. Okay, so that's my little lesson on Lewis diagrams. You can now go ahead and complete that sheet on Lewis diagrams. And I don't have any textbook questions on Lewis diagrams, so just complete the sheet. And then I'm going to move on to my next lesson, chemical compounds, and I will post that a little later as well. All right.